Hello guys, so welcome back to a new lecture of our analog circuits course. And today we're gonna continue our study for the Bean junction. And today is the last piece of the study of its physics, which is the operation under forward bias. So we studied in the last lecture or the last week, Bean junction at equilibrium, in which you just disconnected from any circuit. It's open circuit. It's not connected to anything. And then we studied the Bean junction when you connected to a reverse bias voltage. I mean a battery, and this battery has a positive terminal connected to the N side of the Bean junction, and the negative terminal is connected to the B side of the junction. Okay, and we say that one of the first applications of that new creature, the Bean junction, is to under reverse bias condition is to use as a voltage controlled capacitor. So this is our first application of the diodes, by the way. This varactor or this variable capacitor diode, is just a voltage controlled diode, or I'm sorry, a voltage controlled capacitor. But at the end, it's a diode connected into reverse bias. Today we're gonna study, the Bean junction operation under the last piece, which is forward bias. So we studied open circuit, reverse bias, and now the only available option for now is the forward bias, in which we connect the positive terminal of the battery to the B side and the negative terminal of the battery to the N side. Okay, and why is that? So basically, under equilibrium, we said that there will be positive ions here, negative ions here in the depletion region, and we will have a built-in potential or a built-in electric field that will ban or prevent the motion of the holes from B to N and the motion of electrons from N to B. Good. So our circuits might have, sometimes there is open, sometimes we need open circuit, we need the current not to flow, and in other times we need the current to flow. In that reverse bias condition, there is no current flowing. Okay, so we need something, that allow the Bean junction to conduct current. And to make the Bean junction to conduct current, we need to maintain the motion of the holes, the majority carriers, holes in the B-type region to flow to N type, and the majority carrier of the electrons to flow from N to the B side. Good. So we must overcome, the reasons that prevent them from flowing. So we must put external source that will create a potential. This potential opposite to the potential of the built-in junction, okay, or the built-in voltage. I'm sorry, the built-in voltage or the built-in field. Okay, if you see here, the field here is from positive. The built-in field is from positive ions to negative ions, but the external voltage that we connected right now, which is the V forward, will make electric field in that direction from positive here to negative here, opposing the built-in field, and that will allow the holes to flow from B to N and allow the electrons to flow from N to B. So basically, holes which are positive carriers, will be repelled or expelled by or repulsed, we can say, by the positive terminal here towards the negative terminal. So they will move in that way. These are the motion of the holes towards the negative terminal. And the electrons will be pushed from the negative terminal or expelled or repulsed and attracted to the positive terminal here. So these are the electrons. Okay. Now, where are the current? We have two carriers now moving in opposite directions. Do they make opposite current? So the resultant current will be zero? No. Basically because the current of the holes is in the same direction of the holes. So the current IH is in that way. The current of the electron is in opposite direction to the electron motion. Electrons moves in that way. So IE or IN is in that way, opposite to the electrons, and the same way of I holes. So I holes and I electrons in this, or IB, let's call it IB, are in the same direction. And of course, this forward bias, okay, will just negate the effect of any reverse bias. I mean, reverse bias makes the depletion region to grow, to expand, to widen. This will make it to shorten. So the depletion region will length will decrease. Okay. Good. What else this forward bias will do? It will basically increase the minority carrier concentration on both sides. Why? Because remember now, the holes are moving because we put this external voltage opposite to the built-in voltage. Holes will be moving from N to B in that way. And they are positive. I mean, and so some of them will add up to the whole concentration in the N side. So look, in the equilibrium condition, this was, for example, the concentration of the minority. After connecting it with the forward bias, look now at the minority concentration. It was before, let's say, for example, here it increases to that level. And that one here was, for example, here, and it's increasing to that level. Because electrons are moving from N to B. So they will add or they will increase the electrons of the minority carriers at the B side. And same for the holes. They are moving from B side, where they are majority, to the N side, which are the minority. So also the minority carriers at the N side will increase. Good. Now, there is current is moving, that is moving larger than zero or greater than zero. And basically, there is also voltage drop, okay? Because any device has internal resistance. So we need an equation that relates the current to the voltage, okay? So this is basically the relation that relates the current of the P-N junction to the voltage of the P-N junction. And P-N junction now is called, officially diode. So D here is for diode. And this is the symbol for the diode. And it's easy symbol. So this dash here, this bar is for N, and this triangle is for B. Okay. And this direction, ID direction, is in basically, if we look here, IH is in that way, and IN is also in that way. So the direction of the current from here to here, it's moving like this. So from B to N. If we draw it in another way, you can draw it in whatever way you want. That's fine. You can make it direct, vertical or stuff. So the current again from B to N. And like any other element except the battery, the voltage drop is in opposite direction of the current. So the voltage drop VD is in that direction. So ID in that direction, and VD is just opposite to that. Again, if you draw it in the opposite way, making B here and N here, so ID is flowing in that way, and VD is in that way, from N to B. So this is VD is a diode voltage, or the VN junction voltage. You can call it whatever you want. Here is the diode current. And this is general equation. This is not just for forward and not reverse. No, we can use it in reverse as well, as we will see in a moment. Okay. This equation here has a constant, which is IS. So IS here is a constant. And IS is called reverse saturation current. And in the next slide, you will know why it's called reverse saturation current. It's a current, but in reverse, as you will see. That's why this equation can be used in forward and reverse. This is exponential relation, as you see here. So the relation between the current and the voltage is exponential. It's not linear, like Ohm's law, like a resistor. No, it's exponential. And that will, of course, will make, and the analysis a little bit harder than Ohm's law or normal circuits that we see, in our previous courses. Also, the exponential is a strong function. It's increasing function. Whenever its parameter increases, it will increase. Okay, but it will increase a lot. The rate of increasing is very high, as we will see in the next video. That's why most of the time in forward bias, okay, exponential VD over VT is much larger than 1. Like, for example, 10 to the power of 5 minus 1. This is basically 10 to the power of 5. It's really, you can just ignore this one. Something like this. Example. Okay. So you can just assume this. You can just go, it will not harm to just subtract, but if you may see it in the book like this. Okay.